Welcome back to the ma161 calculus. My name is Götz Pfeiffer and this video is about limit laws. Guessing limits, as we've done it so far, might be convincing at times, but it's not necessarily precise or sound mathematics. It would be better to have ways to calculate limits precisely. With the limit laws we can do exactly that for certain kinds of functions. So here's a list of 5 limit laws. We assume that a is a point on the x-axis. There are two functions f of x and g of x. We assume that the limits of f of x and g of x as x approaches a both exist. Then number 1 is the sum law about the sum of f of x and g of x, and it says that the limit as x approaches a of f of x plus g of x is the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Now the limit of the sum of f of x and g of x can be calculated from the limits of f of x and g of x by just adding them up. So if we know those two, we can compute the limit of the sum. The difference law is similar, just about differences. Well, it says the limit as x approaches a of the difference f of x minus g of x can be calculated as the difference of the two limits of f of x as x approaches a and g of x as x approaches a. Number 3 is the constant multiple law about the constant multiple of a function f of x. The limit as x approaches a of c times f of x is c times the limit as x approaches a of f of x for any constant c. The product law is about the product. The limit as x approaches a of the product of f of x and g of x can be computed as the product of the limit of f of x and the limit of g of x as x approaches a. And number 5 is the quotient law, which says that the quotient, the limit of the quotient as x approaches a of f of x divided by g of x is the limit of x divided by the limit of g, of course, provided that this limit of g as x approaches a is not 0. And that's the limit laws, which allow us to compute, to use these arithmetical operations of addition, subtraction, multiplication and division to compute limits of more complex expressions from known limits. In words, the sum law might be described as the limit of a sum is the sum of the limits. And if you think about it, if f of x is close to a number L and g of x is close to a number m, then it's not hard to believe that f of x plus g of x is close to the sum L plus m. And these limit laws can be proved properly with calculus methods. We won't do this here. We concentrate on the application of the limit laws to calculate limits. When we calculate limits, we use a few more laws or insights. Here number 6, the limit of a constant value as x approaches a is that constant, and this constant expression takes the same value along the x-axis, so the limit is that value. And number 7, the limit of just x as x approaches a is a. These rules are sort of obvious. We take them as given. Then one more ingredient, the power law. As a consequence of the product law, applied n times, or a couple of times, as much as necessary. Now f of x to the power n is f of x multiplied with itself n times. So my suitable version of the product law, the limit as x approaches a of the nth power of f of x is the nth power of the limit as x approaches a of f of x. In particular, if f of x is just x as before, the limit as x approaches a of x to the n is a to the n. And the final one on this list is the root law, which says that the limit as x approaches a of the nth root of f of x is the nth root of the limit as x approaches a of f of x, if that limit exists, of course, and if the nth root of that limit exists. Then we can apply these laws as follows in the following example. Here the function given is 2x squared minus 3x plus 4, and we try to find the limit as x approaches 5 of this expression using the limit laws. We'll justify each step that is taken here in what follows, and what we'll see is a typical procedure that we'll apply frequently as we go along, where we take this complex expression that is a polynomial, and we take this polynomial and decompose it into simpler parts. So we use the notion of sum difference or multiples of functions here, not to make new functions from old ones, but to take the new function and decompose it into older, simpler parts, as follows. The expression we're dealing with here is a polynomial. A polynomial is a sum of multiples of powers of x. So we have all the limit laws to deal with these decomposition steps. First, we look at the polynomial as a sum or a difference of things, and by the sum law and the difference law, and by number 2 and number 1, we can write the limit as x approaches 5 of the polynomial as the difference or sum of the limits of the summands here of these terms. Limit of f of x is the limit as x approaches 5 of 2x squared minus the limit as x goes to 5 of 3x plus the limit as x goes to 5 of 4. That's reading the polynomial as here the difference and there is a sum, and applying the difference law and the sum law, which allow us to calculate the limit of the overall polynomial as the sum or difference, respectively, of the limits of the individual parts. Now, we're still not there yet, but we can now apply the rule number 3, the constant multiple law, to try and compute the limit of 2x squared as 2 times the limit of x squared as x goes to 5, and the limit of 3x as 3 times the limit of x as x goes to 5, and 4 is a constant. We've just seen this here. The limit of a constant is that constant, so this is 4. And then we're left with what's the limit of x squared? Well, there we just had the power law. The limit of x squared is the square of the limit, and the limit of x is, as x goes to 5, it would be 5. So by rules number 9 and 7, we find that this is 2 times 5 squared. The limit as x goes to 5 of x squared is the square of the limit as x goes to 5, which is 5. That becomes 5 squared, minus 3 times the limit as x goes to 5 of x, which is 5, plus 4, which comes to 39 in total. That's how the limit laws allow us to compute the limit of a complex expression, in this case a polynomial, by decomposing the polynomial into smaller parts and applying simple or obvious rules for limits. Like number 6 here, the limit of a constant is that constant, and number 7, the limit of x as x goes to a is just a. If you think about it, what just happened is that at the end of the day, the limit laws forced us or guided us to simply evaluate the polynomial at 5. Now, with this polynomial, 2x squared minus 3x plus 4, it is the case that f evaluated at 5 is that number 39 we just found as the limit of f of x as x goes to 5. Here, we could have gotten this limit by simply calculating f at 5. This is no accident. This is a frequent phenomenon, and we'll look at this more closely in next week's videos. For now, we call this the direct substitution property, and keep this as a note. If f is a polynomial and a is a point in its domain, then the limit as x approaches a of f of x is just f of a. For polynomial, the limit of a polynomial can be calculated by simply evaluating the polynomial at the point a. There are, as we will see, many other types of functions that have this direct substitution property, for example, rational functions. And next week we'll call this phenomenon continuity, which is an important concept in the calculus. Here's another example. The limit as x goes to minus 2 of x cubed plus 2x squared minus 1 over 5 minus 3x, a rational function. Here, step by step, applying the quotient law first, and then the sum and difference laws, and so on. The limit laws guide us to, in order to evaluate this limit, to, at the end of the day, simply evaluate this rational function at minus 2 and find the value minus 1 over 11. Maybe you want to go through the steps for yourself, justifying which limit law you use at each step on the way. Sometimes the limit doesn't exist because the numbers are just too big. We still use limit notation in this case to indicate infinite limits. So here's an intuitive definition. If a function f of x is defined on both sides of a number a, then we write limit as x goes to a of f of x is infinity if we can make f of x arbitrarily large, that is as big as we like, by taking x sufficiently close to a but not equal to a. Similarly, we write limit x goes to a of f of x is minus infinity if we can make f of x arbitrarily large negative by taking x sufficiently close to a. There are also one-sided infinite limits which use the one-sided notation with a superscript plus or minus at the point a being approached. I'd like to illustrate this with an example or two. The known functions, the reciprocal function 1 over x has the property that if x approaches 0 from the left, x goes to 0 minus, then 1 over x becomes larger and larger negative. Here the graph goes off to minus infinity. And if we're approaching x from the positive side, if x goes to 0 plus, then 1 over x becomes larger and larger positive. The graph here goes off to the positive side. That's one-sided infinite limits. One is minus infinity, one is plus infinity for the reciprocal function 1 over x. The function 1 over x squared, on the other hand, approaches infinity or takes larger and larger value. The closer we choose the x to 0 on both sides, so here the limit as x goes to 0 of 1 over x squared is infinity. In both cases, we call the vertical line through this point where the function is not defined a vertical asymptote. And the vertical line with the equation x equals a is called a vertical asymptote of the curve y equals f of x if at least one of those four statements is true. The limit either from the right hand side or from the left hand side, either to plus infinity or to minus infinity of f of x is f of x, this should be the limit of f of x. And the limit of f of x as x goes to a plus is infinity. I'll insert f of x here in these four places in the notes. So if the limit of f of x, one-sided or two-sided, if the two are the same, is either plus or minus infinity, we call this vertical line a vertical asymptote. We've seen examples of this before. On the x-axis, the y-axis x equals 0 is a vertical asymptote of y equals 1 over x squared. We've just seen that. And this is a function that satisfies 1 and 2. The line x equals 0 is also a vertical asymptote of y equals 1 over x, because their properties 1 and 4 are satisfied. The tan function as the quotient of sine x and cosine x is not defined, and these values x, where x is n plus 1/2 pi for any integer n, and there we find an asymptote, a vertical asymptote in these places because conditions 2 and 3 are satisfied. X equal to 0 is also a vertical asymptote of the logarithm, the natural logarithm ln x here, because that satisfies property 3. And the graph y equals 2x to the 4 minus x squared plus 1 over x squared minus 4 has two asymptotes, x equal to minus 2 and x equal to 2. We've seen those before. Maybe you take your time and find those graphs in the previous lecture notes to see the vertical asymptotes in these examples. So now we've seen that on the positive side, we've seen that the limit as x goes to a of f of x may exist even if the function f of x itself is not defined at a. But then some limits certainly do not exist, and sometimes limit notation is used to indicate why a limit does not exist. And we've seen these one-sided limits, for example. If the left-hand limit is different from the right-hand limit at a, then the limit of f of x as x approaches a does not exist. Also, the infinite limits that we've considered now are instances of limits that do not exist. Infinity is not a number, and the limit as x goes to a of f of x does not exist if it's plus or minus infinity. And finally, the limit can fail to exist if there's no specific value that the function approaches, as in this example of the limit as x goes to 0 of sine of pi over x. First of all, because we're not allowed to divide by 0, this function is not defined at x equal to 0, but that doesn't matter for the limit consideration. We could list values. If we evaluate this function f at negative powers of 10 to the minus n, then we're looking at the sine of 10 to the n pi. This should be the sine of 10 to the n pi, which is 0 for all choices of n. So here we find closer and closer to 0 values of f of x that are 0. Still, 0 is not the limit, because the sine keeps oscillating between minus 1 and plus 1. There is no number L such that f of x is close to that number for all x close to 0. Neither does this f of x become arbitrarily large, positive or negative, nor do one-sided limits exist. So here's an example where the limit genuinely doesn't exist. That's it for now. Next week we'll look at continuity.